place to look at how energy is converted from potential.
As Christina goes back and forward on the swings, she does not know that the laws of kinetic and potential energy are acting upon her at every moment. The principle of conservation of mechanical energy states that the total mechanical energy, E, equals kinetic energy plus potential energy, assuming that there is no external work on the object. Here we can see an image that shows the movement of Christina from point 1 to point 2, point 3, point 4, and point 5. We know that the mass is 60 kilograms, the height is 10 meters. From point 1, we can see that the potential energy can be calculated to 6,000 joules. Kinetic energy is 0 because there is no velocity. At point 3, the kinetic energy is at its maximum. However, potential energy is at 0 because there is no height. After knowing that kinetic energy also has to equal 6,000 joules because there is no potential energy and kinetic energy has to equal the total mechanical energy, now we can find that velocity equals 14.14 meters per second. At point 4, there is potential energy and kinetic energy. By knowing that the height is 5 meters, we know that the potential energy equals 3,000 joules. By knowing that, we know that the kinetic energy also has to equal 3,000 joules because both of these have to equal 6,000 joules. By that, we can find that velocity equals 10 meters per second. Now that we've found the potential energy and kinetic energy from point 1, point 3, and point 4, we can now find, we now know that point 2 and point 5 are similar to these. Point 2 and point 4 have the exact same potential and kinetic energy, assuming that this distance is 5 meters, similar to this one. We also know that point 1 and point 5 are exactly the same, assuming that the height, 10 meters, is also 10 meters over here.
As Alejandro is saying at the top of the slide, he has all potential energy and no kinetic energy. When Alejandro is at the bottom of the slide, he has all kinetic energy and no potential energy.
A lot of what scientists call potential energy, or the energy of position. The slightest puff of wind, and that potential energy will immediately start being transformed into kinetic energy. That's how the energy of position becomes the energy of movement. Uh-oh, don't look now. But it's time to use some more kinetic energy to do some more work on that giant. Whoops. Hold on. What's happening? Let's do that again in slow motion. The stone lost more and more speed as it left your sling because of the force of gravity trying to pull it down. The higher it got, the slower it went, and the less kinetic energy it had. Until at last it came to a complete stop and had no kinetic energy left in it at all, and therefore no work in it, and no force that it could exert on the giant. But where did all that kinetic energy go? Is it lost forever? No. It's being transformed into potential energy. The work that the little man put into slinging the stone is now stored up in the stone. But of course, in reality, the stone only stops for a split second, and then immediately starts coming down again, until it has got back all the kinetic energy.
When the ball is in the air, it has both kinetic and potential energy.
As you can see here, this unskilled player wasn't able to deliver enough kinetic energy to the ball in order for it to reach the other player. As you can see, he really sucks. Here you can see that the ball has enough kinetic energy to reach the other player. However, the umpire is unskilled enough to catch the ball. Here, the ball has too much kinetic energy and goes too far.
And there are two different pitches. When I throw a baseball, I probably throw it around 20 miles an hour if I were to throw it. I'm not a very good thrower. But a really good major league pitcher will throw it at 100 miles an hour. And so let's figure out how much kinetic energy would be in one of my throws and then those of a pitcher in the major leagues. First of all, we have to figure out the mass of the baseball. Mass of a baseball is 0.145 kilograms. And since we're doing kinetic energy, the only other value that we need is the speed. And so if you throw a 20-mile-an-hour pitch, that's roughly 9.0 meters per second. Remember, on all these, we always have to convert it to meters, or meters per second, excuse me, if it's a velocity. A 100-mile-an-hour pitch, then, is roughly 45 meters per second. And so first of all, let's figure out how much kinetic energy my pitch would have, a 20-mile-an-hour pitch. We use the equation 1/2 mv squared, where m is 0.145 kilograms and v is 9.0 meters per second. We then take that times 1/2 and square the velocity, and I get, using significant digits, 5.9 joules of energy. Now let's try the faster pitch. It's 100 miles an hour, so that is 45 meters per second. So we're going to use 1/2 mv squared. Our mass remains the same, or it's 0.145 kilograms, except our velocity now is 45 meters per second. If I multiply that across using significant digits, I get 150 joules of energy. Again, when I pitched at 20 miles an hour, it was only 5.9 joules. And so even though that pitcher is throwing it 5 times as fast, he's getting roughly 25 times the amount of energy out of that pitch. And that's why, if you look at the equation, the velocity being squared is super important to understand that. And so you can solve complex problems.